All right, why don't we get going? Thank you, everyone, for joining us today. We're going to be talking about the effects of land-based wind turbine upsizing on community sound levels and power and energy density. This webinar is a derivative of the journal paper, which has been released a few weeks ago. Just a few little housekeeping notes first. Everyone on this webinar is muted, but we want to hear from you. So please try to find the Q&A window. It's usually at the lower part of the app, and submit questions via that Q&A window. We will be monitoring those questions throughout the webinar and can answer them during that time if possible. But as well, we'll use that as the fodder for the open Q&A portion at the end of the presentation. This webinar will be recorded. So if a colleague of yours was not able to join us today, they will be able to get the recording after that. We will be sending it out to all the registrants tomorrow or later today. As well, this PowerPoint will be shared with everyone who has registered. All of this will be posted on our landing page. If somebody will drop that link into the chat, that's where the presentation, the paper, the webinar, all of that will be housed indefinitely. Finally, before moving on, I'd just like to thank the Wind Energy Technologies Office of the U.S. Department of Energy and their support for this project. We couldn't have done it without them. This is the team. Not a very diverse team in terms of facial hair, except for me, but crackpot group of engineers and specialists. It's been a real pleasure to work with them on this project. Everyone is on the call. In terms of presentations today, I'm going to be passing the mic at some point to Ken Kaliski, who's going to present as well, and then everyone will be around for the Q&A portion. Ryan Darlow is a project engineer from Vera Renewables. He's on the call, as well as Ryan Hawk, who's an acoustic consultant from RSG. Joe Rand, my colleague from Berkeley Lab, is an energy policy researcher. And Ken Kaliski, who I mentioned, will be sharing the mic duties with me as a principal and noise control engineer from RSG. Quick disclaimer, the opinions and views of us, the authors, are not necessarily those of the state of California, the United States government, or the University of California. They are our opinions alone. This is the quick agenda for today. We're going to cover some background, the data and methodology used for the analysis. We're going to dive into results and then give you some takeaways that you might use after this presentation. So in terms of the background, why is this an interesting subject? Why was it that we became interested in studying these things? This figure tells a lot of the story. As you can see, the hub height and rotor diameter of installed US wind turbines has been steadily climbing over the last decade or more. The current height of installed capacity, based on just the first little bit of 2023, is 549 feet or 169 meters. That's very tall relative to where we were even just a few years ago. The capacity of these turbines has also increased. You can see it's really a very sharp increase, with current averages for 2023 being at 3.5 megawatts. A recent survey done by my colleagues at Berkeley Lab found that experts predicted that those trends will increase, and we surely have seen no sign of that abating. The FAA permit data, which we reference in the paper and we include as part of the land-based wind market report that the LBNL puts out each year, shows that future turbines will even be taller. As well, one other fact to note is that the specific power of turbines has been steadily declining, though relatively flat more recently, which is a metric to use as you think about the availability of that turbine to produce power and its efficiency. It's a sort of a metric for its efficiency. So with the growing rotor diameters the tips of the turbine, the tips of the blades are further away from the rotor. If the rotor is spinning at the same speed, that means those tips are moving even faster. There's an upper limit for the speed at which those tips can be moving, but they have been steadily increasing. One way to slow the tip speeds down is to slow the revolutions per minute of the rotor, and that has indeed occurred. But that has not fully offset the increase in tip speed that we see in the purple figure. More recently, maybe we've seen a little adjustment as revolutions per minute have come down, at least through 2020, which has slowed down the tip speeds to some degree. Wind speed, interestingly, has remained fairly flat. With larger rotors and higher hub heights, you are able to gain access to speeds of winds that weren't otherwise available. And so it's reasonable to assume that these newer turbines that are taller would be placed in wind regimes that are lower average wind speeds, but that's not actually what we've seen. Instead, we've just seen a proliferation of these same taller turbines across the country. Tip speed, importantly to note, though, is considered a key contributor to sound emissions. And at this point, I'm going to hand it over to Ken to talk about those emissions.
Thanks, Ben. So what I'd like to talk about is sound from wind turbines, how the sound is generated, and then give you a sense of why these changes in the structure or the height and the length of the blades and so forth generate a different sound. So this is a picture of a study that was done way back in 2004 on an older generation of wind turbines, sort of characterizing where the sound is coming from wind turbines. So on the right, I took these decibel levels and essentially made a pie graph. And what we see on the right is the largest contributor of sound is aerodynamic. So it's the wind going over mostly the blades. The gearbox is secondary, and then there's sort of miscellaneous other sources of sound from the wind turbine. It's likely, though, that aerodynamic sound is increasing from these modern generation of wind turbines because there's just more blade area. The tip speeds are higher, and so we expect that aerodynamic sound is a much larger component with larger wind turbines. And the next slide, please. And we see that if we look at the installed capacity of wind turbines in the years from 2006 to 2020, we could see that in 2006 we had an average sound power level. Sound power is a metric of the sound energy emitted by the wind turbine of about a little over 104 decibels. And by 2020, that increased to a little under 109 decibels. So almost a 5 decibel increase over that span. And we can also see that the range of sound powers have also decreased. So we're not getting brands or manufacturers generating very high or very low sound emissions. Now, I'm going to caveat this by saying that this graph does not include the effect of serrated trailing edges or noise-reduced operations. So in actual fact, because serrated trailing edge implementation in the projects are becoming more common, that the sound power of the installed capacity is likely to be flattening out. So in 2019, these serrated trailing edges were installed in about 25% of the wind turbines, and that's increasing very rapidly. And we're saying that it's likely going to be 100% in the future because, at least for these large turbines, they are being offered to their customer base as a standard feature. So if you buy a wind turbine, it automatically comes with these serrated trailing edges. In addition to serrated trailing edges, we have noise-reduced operations that can lower the sound emissions from a wind turbine, and you're basically slowing if you need it under certain conditions, like certain wind speeds or certain wind directions, you can lower the rotational speed of the wind turbine and reduce noise. But it's only used in specific situations because while it reduces noise, it also reduces the power output of the wind turbine, and it adds stress to the wind turbine. So it has an impact on the life cycle of the wind turbine. Next, okay. On the picture on the right, this is just a reinforcement of what you saw on slide 8, where you have most of the sound being generated on the sort of the furthest third of the wind turbine blade, and then some by the hub, and then the rest doesn't show up in this picture. This is an acoustical camera, which takes a picture of the sound emissions from the wind turbine. But why does the sound from wind turbines matter? Well, it's a design constraint in most US areas, and certainly outside of the US as well, where you have noise regulations, you have people concerned about noise, you have people concerned about the height of the wind turbines. So it's something that is definitely very much considered in permitting wind projects and after they're permitted as well. But also, we have a constraint. You know, we have a limited amount of transmission. Most of these projects are near transmission lines, and so we're likely to see these wind turbines go into areas of higher population densities. And so looking at the impacts on people of sound is going to be more important. So we have an algorithm here. We have, I'm not going to say louder turbines because that's at the receptor, but we have turbines with higher sound power. We have longer blades. We have higher hubs and higher tip heights. So that results in larger setbacks from people. In the same time, we have higher nameplate capacity. We have higher capacity factors. So if you put all these things together, what are the impacts? How does sound at receptors change, and how does the energy generation from a wind project change? So Ben is going to take it from here and talk about our data methodology and results.
Yeah, thanks, Ken. So we had this situation and we wanted to better understand how these various factors that are kind of pushing and pulling against each other might ultimately net out. We want to examine, therefore, changes. Well, so we really are looking at this through the lens of the community. You know, how would a community fare in those scenarios, at least as regards sound, but some other things as well. And so our approach was to sort of do all of this on a desktop level. I mean, I guess in the perfect world, you could just go out and develop a bunch of projects and check it out yourself. And in fact, there are projects out there that have these modern turbines in it. But we wanted to start at the desktop and do relatively simple analysis. And that's what this is. But it does tell us some things that otherwise we wouldn't have been able to do. So we're using a desktop software technique, which is not unlike developers use when they are siting or micro-siting projects in communities. We take two previously built sites, which I'll talk about in a moment, and we basically redevelop them on this desktop software using 3 epochs of turbines. We use turbines from the then period, which is basically the past, if you will. We use turbines from the now period, which is more current. And then we're going to look at turbines that will be installed in the future. And having the baseline from then, looking through now, and then looking to the future should give us a sense as how things have changed over time and will change in the future even further. Because we have a set of sites that I'll describe in a moment, we're going to look at those sites and look as we move from then to the future, how the numbers of turbines change, how the capacity of the total project changes, how the annual energy output of the project changes, and how our community sound levels, those experienced as or estimated to be experienced at the participant and non-participant homes, how do those change over time or over these epochs? And then finally, how does the land use itself change in these various projects? Hopefully, we can get some sense as to whether communities will be better or worse off with these future turbines based on only these criteria. We're not considering a whole host of other things, but based on just these things. So as I mentioned, we have these three epochs of turbines, and we started with the then period. Those are the most popular, most frequently installed in the United States for three OEMs. Those are the most largest OEMs based on market share in the United States, and actually the whole world except for China, when you don't consider China. Those OEMs, or original equipment manufacturers, are GE, Vestas, and SGRE. So the most frequently installed turbines in the US of those three over the last decade, or at least 2011 through 2020, was the GE 1.577 with 77 meter rotors, the Vestas 1.65 V82 with 82 meter rotors, and the SGRE, or Siemens Gamesa Renewable Energy 2.393 with 93 meter rotors. The total height of those then turbines is 122 meters. The rated capacity across those three turbine models is 1.8 megawatts. The specific power, which I mentioned before, is sort of a measure of efficiency, is 324 watts per meter squared. The lower that specific power is, the better it is at garnering the power from the wind and converting that into electricity. And then the sound power level, as Ken mentioned, is 104.3 for those three turbines. Then we wanted to look at the now epoch. That's the most popular in the last 2 years in the US, or 2019 to 2020. And you can see those turbines listed there. That average height is 148 meters. That average rated capacity is 2.4 megawatts. The specific power is 226, a big drop from the then period. And as well, the sound power level goes up to 107.7. As Ken mentioned, that's been steadily climbing. Now, if we jump to the future, as Ken mentioned, the standard, as we heard from talking to the original equipment manufacturers, is that these turbines are going to be installed with these serrated trailing edges. And the picture kind of shows them there at the end of the blade. Well, we knew that was going to be the case, and we'd have to factor that into our future analysis. But we wondered what would be the effect of putting them on the now turbines, because they are being installed on some turbines that are being installed now. And so we were able to get models for GE and Vestas to do that. We weren't able to get an SGRE model for with the serrated trailing edges. And the averages for those turbines are effectively the same, except for the sound level. You can see the sound level drops, sound power level drops from 107.7 to 105.8. Now, focusing on the future, these are turbines that were, at the time we started this analysis, not yet installed, but we were told were going to be installed. But they have already now been installed. There are examples of these future turbines in New York, Texas, Illinois, Nebraska, and West Virginia. For the GE turbine, it's a 3.6 137. For the Vestas, it's a 5.6 V162. And for the SGRE, it's a 5.8 170. The average height for these future turbines is 202 meters. So a, 33% increase in height over the now period. The rated capacity goes all the way to 5 megawatts, much bigger generator on these turbines, doubling from the now period, and a slight increase in the specific power. That's in part because of the capacity of the turbine is increasing faster than the rotor diameter. And the sound level, in part because of the serrated trailing edges on the turbines, goes down to 105.3, still louder than the then period, at least sound power level, but not as loud as the now period turbines. So these turbines make up the set of turbines we're going to look at these sites. I mentioned we had 2 sites. These are actual developments where we got a hold of the parcel shape files. We knew where homes were as well in these locations. We could see, based on satellite imagery, where turbines were actually located. And when they were located there, that became a participating parcel. As well, we modeled the sound in these locations based on those installed turbines and found that some nearby parcels that didn't host a turbine were at a sound level that was above what would normally be expected for neighbors, and therefore we included them in the participating parcel group. So those are the pink parcels here. That is the land constrained area that we redeveloped with all of these 11 turbines over and over again. Each of the receivers could be participating or non-participating, are shown in black dots on these two figures. So this is the group that we're really looking at. We're constraining the site, and we're saying, how will things change if we constrain the site and try to get the developments built at these places? So we have a number of rules that we used in the development of these sites on the desktop. We first assume that total turbine height is hub height plus half of the rotor diameter. And we use that to set the turbines back from the property and roadways using a metric of 1.3 times that total height. We space the turbines out based on what is conventionally used of 8 rotor diameters row to row based on the prevailing wind direction. So this is sort of to give them enough space so that there aren't big losses due to wake effects. But on side to side, we use 5 rotor diameters to space them out there. They obviously don't always operate in the prevailing wind direction, so we take that into account with the 5 rotor diameters side by side. There are applied noise regulations in these models, a 50 dBA LEQ 1 hour max for participating residences, and a 45 dBA LEQ 1 hour max for non-participating residences. Remember those that are on the white or the pink parcels. And then finally, we optimize for annual project output, megawatt hours per year, while respecting these various other restrictions. Now, that isn't the only way to develop a project. You might want to maximize profitability, or you might be constrained in terms of the amount of power you could put out locally. And so you would just want to max out the hours that you're putting out power without getting curtailed. But it is a very common way to optimize a project. We don't consider wind turbine availability. So we don't consider if the turbine is taken out of service, as it often is, maybe a few times a year for regular maintenance. We do consider wake losses for turbines that are behind each other, but we don't consider grid availability, just kind of what I said. They might curtail at that location, or transmission losses. Maybe the spur line is very long and there might be some losses as we move to the transmission grid. So we don't consider those things, but we do consider wake losses. And that gets us to our results. And I can start talking about that. So I think I'm going to take the mic here for a little bit, Ken, and then pass it back to you when we get to the sound slide. So what did we find? Well, obviously, we found that turbine heights increased by, in fact, 65% or 80 meters as we moved from the then turbines that I showed on the previous slide to the future turbines. Because of these larger turbines and the setback requirements from property lines, and also the relatively louder turbines based on the sound power level, we see that fewer turbines can fit in this land constrained area, a drop of 60%, in fact. So very few turbines relative to what we started with in the then period. We see as we move from the then period through the now, and now with serrated trailing edges and future with serrated trailing edges, that we have an initial dip in the nameplate capacity, which is the total nameplate capacity for the project by basically adding up every turbine and its individual capacity, to an increase in nameplate capacity in the future period by roughly 11%. So even though we're dropping the number of turbines, we still see an increase in total installed nameplate capacity. But the big increase comes from project output. Remember, we're trying to maximize the output. We've got 60% fewer turbines, but we see almost a 60% increase in the total project output for projects that are built with modern turbines or future turbines versus those that were installed in the then period in the last decade. One thing you should note, which I'll reference later, is that this increase in nameplate capacity and this increase in project output would probably mean an increase in some of the financial benefits for the community. A lot of them are based on nameplate capacity or project output, and that could be not only payments to landowners, but as well way taxes are collected if they are collected in communities. So this might mean greater economic benefits for communities, but given the same amount of land. But sound from those turbines is a different story and was measured differently. And Ken's going to cover the effects we found for sound at those various receivers I mentioned earlier.
Thanks, Ben. So this chart looks a little bit different than the previous one, so I'm going to spend a little time going over how to interpret it. So on this horizontal axis, we have the then sound levels. So for all, it represents, say, for example, all the receptors that had 35 decibels in the then scenario. The y-axis, or the vertical axis, is the change in sound levels from then. So I'll give you an example. These three curves represent in yellow, then to now, in orange, then to now with SDE, and then in blue is the then to future with SDE. So, for example, for those who were receiving 35 decibels in the then scenario, the then to now, you're getting maybe a half a decibel drop in sound levels now. And then with serrated trailing edges, you probably get another half decibel improvement. But the then to future, we're getting almost a 3 decibel drop in sound. So we can see for sure that the average sound level for people who were experiencing on the lower end of the impacts are improving by about 3 decibels. But we also wanted to see, does this hold true for those who were receiving the highest sound levels? Because when you're developing a project, a lot of times you're working on reducing the impacts for those highest people receiving around what would be the standard in this case, 45 decibels for non-participants and 50 decibels for participants. So you end up with more than your fair share of impacts around the sound standard. But we did find that even with those who were impacted before or at the standard, there's still a reduction in sound levels of about 2 decibels in the future scenario. So we're still getting improvements of those people who are mostly impacted. The dotted lines on the right are for participants. And so we even see that for participants, for the future scenario, we get a drop in the sound impacts. And what's interesting is that for those with the highest impacts, those around 50 decibels in the then scenario, those are getting the most benefit. So close to 3 decibel drop on average to the modeled sound levels. Ben?
Yes, I'm taking the mic back.
Yep.
Okay, so the last bit of results here, I mentioned that we wanted to look at land use. And you've seen this. We discussed that there are much fewer turbines in this land constrained area as these turbines increase in height and should go from then to future. Because of those fewer turbines, there are fewer host parcels, right? There's just going to be less places for those turbines to go and less parcels that will host them. And no surprise, we see an increase in the number of non-host parcels of approximately 43%, and a corresponding 47% decrease in the number of host parcels. And one last little effect is that the host parcel size increases by a little, not dramatically, roughly 12%. And there's no surprise there either, right? We have larger turbines here that have to be set back from the edges of the parcels. And so certain parcels that might otherwise have been able to squeak by and be a host at some of our sites for slightly smaller turbines just can't qualify as a host for these much larger turbines that would be installed in the future. So we see parcel sizes increasing as well. So one of the things to note that we can infer from this is that there are fewer landowners that are going to be hosting parcels. Those landowners themselves will have larger parcels as we move from then to the future. Now, often it's those landowners that are the primary beneficiary of payments to landowners. They are the hosts. And in the past, often they were been given the lion's share of the benefits in terms of financial remuneration. Other agreements might be signed with individuals that might have been a possible location for a host turbine, but ultimately didn't get it in the final shakeout of where the turbines would go. They might be getting some remuneration, but not as much as the host. And as well, the neighbors nearby any possible locations or eventual locations of turbines might be getting something, but a much smaller payment. So I think what's important to note is as we move from the then into the future, we are going to be in a scenario where we have fewer and fewer of those individuals that are hosts. And therefore, there's a possibility for greater disparities between the remuneration of those nearby, whether there are possible hosts that just didn't get turbines or neighbors. And so it's just kind of a cautionary tale that if we are hoping for more distributive equity of projects as projects go into communities, this will need to be thought through very carefully. And in fact, as we can discuss in Q&A, if you're interested, some developers are already responding to this fact and adjusting the way that they develop projects and remunerate communities based on it. So that gets us to the end of the presentation. Wow, we're doing great on time. So I'm just going to read through these takeaways. We want to be careful that we are clear about what our results say, but also what they don't say. So we're seeing significant turbine scaling is occurring with no real sign of it abating, at least for terrestrial turbines that we had studied. Despite increasing RPMs, we see a steady increase in tip speeds and turbine sound levels. The increase in sound levels and tip speed might indicate, we wondered, that hosting modern turbines means that higher levels of turbine audibility will be experienced in communities as compared to those that are hosting older turbines. But we find that increased turbine heights and sound levels increase the setbacks from those homes. And even when there are participating landowners, we see a drop in sound levels. Our analysis finds that modern turbines to be deployed in the next 3 to 5 years and actually already being deployed potentially will significantly decrease the sound levels community experience while simultaneously increasing the installed capacity and annual energy output. The increases in these capacity and output will likely, or maybe will lead to increased tax benefits in the community, but we can't say that for sure. And obviously it has a lot to do with the individual taxing regime in that community and how, whether there is one at all. As well, we note that the concentration of fewer turbines on fewer and larger parcels might create disparities between those receiving and those not receiving substantial benefits from the project, unless those are addressed through other means. And finally, a big caveat here, we do not consider the visibility of turbines in this analysis, but it's clear to say that as turbines increase in height by 60%, as we found, they are going to be a lot more visible to others in the community and further away. It's going to enhance the ability to see the turbines from much further away. I will also note that the FAA, the Federal Aviation Administration, has different requirements for lighting for turbines that are taller. So, for example, an additional light might be required on the nacelle for turbines greater than 500 feet. And turbines that are greater than 600 feet, 650 feet will actually need a light or a set of lights along the tower as well. So a lot more lights will be visible at night. There are ways to mitigate this, but this is something we don't consider, but should be taken into account as an additional caveat of this analysis. Finally, to note is that we don't analyze but 2 facilities and those 11 turbine models. There are lots of other turbine models. There are lots of other facility locations around the country and around the world. We don't consider them. It could be that the results are going to be different for those facilities than we found here. So we accept that that admission and that limitation to applying this work elsewhere. But with that, I will end the presentation, open it up to questions. We did post in the chat the link for the site, but you can find it here. Effects land-based wind turbine should bring you to the landing page. And as I mentioned, this presentation, the recorded presentation, the paper, and a quick distillation of the report are all available on that landing page. So with that, let's turn to questions. I think our colleague Joe Rand is going to be the moderator of the session and feed questions to us if he can't answer them himself.
Yeah, thanks, Ben and Ken. Great presentation. And before I dive into the questions, I did want to clarify that I wasn't actually able to drop that link into the chat as I don't have the ability to chat to all participants. So Ben or Ken, as hosts, if you could do so, that would be great. And we do have a bunch of excellent questions that came in. Ryan Hawk at RSG and I have been answering some of them. So if you submitted a question, it may have already been answered. Check out that in the Q&A. And if you're curious about questions that have been answered, you can see those there as well. But let's get to the open questions that we haven't responded to yet. So starting just from the top, Ben, are you aware of similar studies that explore these kinds of questions for offshore wind, specifically thinking about marine noise levels and kind of shoreline community power impacts?
I am not, but I will give a shout out to NREL, the National Renewable Energy Lab. Our analysis is at a very fine resolution looking at individual projects. They are trying to build a model that takes into account sound at a much broader level. Ken is working with them on that project. I don't believe that is offshore. I think that is terrestrial only, but it gives them tools potentially to expand to that. But I'm not aware of that. But let me see if Ken has an idea here. He's one of the folks that is called on to better understand what possible impacts sound from turbines would have on communities, and wondered if you've looked at offshore turbines in that context.
No, we haven't looked at offshore in that context, and I don't know that there's a lot of people doing work in that yet, but that is certainly coming. But I haven't seen any papers on it, on that specific subject.
All right, I propose we move to the next question. So yeah, I think there's a great question here talking about amplitude modulation. So as turbines get larger, we potentially have greater wind shear, or the difference in wind speed across the rotor that might be more prominent with larger rotor diameters. Could that lead to kind of greater modulation in the sound, while still having, you know, the turbine placement and the receivers, you know, being under the decibel limits that are enforced? So did we think, or, you know, Ken or others, I will just note that, you know, there has been other research that potentially links sound annoyance a little bit more to this idea of amplitude modulation, rather than just the kind of the strict decibel level. So Ken, do you want to weigh in on that?
Yeah, maybe Ryan Hawk can also answer, based on a previous study, about whether the tip or the blade size affected annoyance to amplitude modulation. But you know, it's certainly a good question, because you have a larger swept area of the rotor at the top, so you have a higher shear, basically, of the top of the swept area has higher wind speeds, and the lower portion of the swept area has, you know, relatively low wind speeds. So the question is whether and how the turbine can optimize to take advantage of that through you know, differentially pitching the blade as it sweeps through the the top and the bottom parts of the rotor to take advantage of the low winds and to prevent stalling and to prevent stalling in the low winds and to take advantage of the higher winds at the top. So I don't know of any studies that have really compared amplitude modulation to between these very large or relatively large turbines in the future that we're looking at, and the then or not even now scenarios. Ryan, do you remember what the results were for our public acceptance and wind study related to amplitude modulation or rotor size and annoyance?
We didn't study amplitude modulation per se, but I guess
we looked at rotor size as an annoyance, and so I guess that was the question.
That may, if I recall correctly, yeah, that may have been a significant variable for annoyance. Maybe it was minorly significant, but I guess what I would say about the larger turbines is that there may be a concern of when there's amplitude modulation, that now you have the serrated trailing edges, which in typical operation do a great job of reducing sound level, and certainly will reduce the sound level over a long period of time or for typical operation. But, once you have a different sound generating mechanism through amplitude modulation, that's kind of stepping around those serrated trailing edges, because amplitude modulation is not trailing edge noise. That there could be some concerns for sound levels similar to turbines without serrated trailing edges, for example. So it's it's certainly something to keep an eye on with larger turbines.
Great, thanks, guys. Ryan, maybe I'll stick with you here. Just and we did answer a couple of these questions, but just since there were more than one, and I want to make sure all attendees are hearing this, a few folks asked about whether a decrease of 1 decibel is really perceptible to the human ear. So what's kind of, when we say an average decrease of 1 or 2 or 3 decibels, is that really noticeable? Yeah, go ahead.
Yeah, I could take that. Yeah, I mean, generally a 1 decibel increase or decrease is not perceptible. And we generally say that a 3 decibel change is just perceptible to humans. The caveat there is if we talk about the quality of the sound or where in the frequency spectrum that sound is located, because we could have the spectrum being shifted higher or lower. And so one possible application or example of that is for larger turbines that may have more low frequency content. They may be more perceptible indoors, for example, because you have this low frequency that is more perceptible indoors because it's not masked by the rest of the anthropogenic noise and wind, the geophonic noise, everything that's outside. So I guess, did that answer the question?
Yeah, I think so, Ryan. That's great. Maybe I'll go ahead.
Sure. Just one thing to note, and I just dropped it in to the chat for everyone to click on if they want to. Ryan was referencing a survey and analysis that we did looking at sound around wind neighbors, and so that's there for folks to look at. But one of the interesting findings from that is that we found a very strong relationship between people's claimed ability to hear the turbines. They said, yes, I can hear the turbines from my home, or I can hear them from my property, and the modeled sound level using this rating, same kind of rating, the dBA or sound pressure level experienced at their house. We did not find a strong relationship there in using those same survey respondents to that, an increase in that level once they could hear it and their annoyance. So to some degree, it agrees and disagrees with what was just said. Surely the sound level that people are experiencing is something that's perceptible. Now, we did find a pretty steady relationship between the increased level and increased perception. And I don't know if we broke it down by decibel or not, but clearly, as we saw more and more modeled sound at various receptor levels, we did see increased perception of that sound. Like I can hear it amongst our survey respondents. So just a little bit more context there, and please go ahead and look at that paper for additional insights in that regard.
Let me add to that, typically, 3 decibels is not much of a difference. But when you're very close to that audibility threshold, or in other words, that if you're at 40 decibels and the background is, I'm just going to use an example, say 40 decibels, you might not notice the wind turbines very much. But then if you go to 43 decibels, it comes out of the background more, and so it's more audible, and so that's where these little changes have an impact. We're talking about sounds, it's 35, 40, 45 decibels that are very close to background. Also, it also matters because you are near the noise limits. So a 1 decibel increase in sound power may not sound like much, but it may have a very substantial impact on your ability to develop these turbines or the output from a wind project. So if you are able to reduce the noise impact by 1 or even 2 decibels, you might be able to increase the capacity of your project.
Yeah, those are excellent points, Ken. Thanks, guys. Well, I wanted to kick a question to Ryan Darlow. We haven't heard from you yet, and we've, I think, got what I'm going to call a 2-part question. So there'll be part A and part B, and they both come from Owen Roberts at NREL. So part A, can you speak about the assumed tip height setback from homes or occupied structures? And then part B, when we kind of think about the way in which we developed these sites and optimized them to maximize annual energy output, was that applied to the then scenario equally as it was in the now and future? And also, is that is it possible that kind of is suboptimal from a developer's financial perspective? So yeah, Ryan. Thanks.
Thanks, Owen. So the first question about the total height, we used the 1.3 total turbine height multiplier, as this slide here shows. And that's across the board, but also on top of that, there were 2 other setbacks, if you will, which were the participating and non-participating sound thresholds. So those will.
Uh-oh. Might have lost Ryan Darlow. I'll try to pinch hit here. Can you guys hear me?
Yeah, I can hear you, Ben.
Okay, it's not, so maybe we'll get Ryan Darlow back in a moment here. And Owen, I hope it do you justice. Yeah, we have the sound regulations that we are applying at the locations. The maximum sound power, maximum annual project output was used for all projects, then, now, and future. We basically are doing the exact same thing for all of them. So we have ability to compare them apples to apples. And I guess the last question was, how might these projects be different, and would we have different results if we used a different way to maximize? So the one you mentioned was profit maximization, and I think this is a great question for Darlow. I'm actually not exactly sure how that's going to affect things, but we could imagine that you want that project to produce power during peak power times. If you're selling it out on the market, you want to keep it operating as much as possible. Might be a little bit of different considerations, surely, if there's capacity constraints for that project, which we don't basically consider. So I will say that there are a number of variables that could mean different outputs, but maybe when Ryan checks back in, we can have him pick it up from there. Unless others want to venture a hazard a guess at how, for example, a profit maximization strategy for siting would be slightly different in terms of our results for annual project output maximization.
Yeah, I mean, Ben, I think you covered it well. A developer citing a project is going to be optimizing across many variables, probably not just annual energy output. And but I think that for the purpose of our study, optimizing for annual energy output essentially means fitting as many turbines in the given space as possible, assuming we're spacing appropriately for wake losses and so forth. So I think we're kind of potentially looking here at a worst case scenario effect. That's what I would say. There were a couple questions. Someone was asking about direct drive wind turbines that do not use a gearbox. And Ryan, I think maybe you answered one. But Ken or Ryan, if you want to chime in, we didn't look at any direct drive turbines in this study, but how would that change the equation here? Obviously, direct drive turbines are maybe more common for offshore wind development, a little bit less common for land-based wind, but nonetheless, any kind of qualitative, we don't have quantitative data in this case since they weren't included in the study, but Ken, you did mention that most of the sound comes from aerodynamic impacts and not necessarily the gearbox, but yeah, feel free to chime in there.
Yeah, I mean, most of what our results are based on the sound pressure level or the sound power level of the turbine, so that is mostly what we're looking at. I think direct drive might affect the tonality of the nacelle if that is an issue. Tends to reduce tonality, but I assume that these results could be applied to any type of wind turbine or any type of wind turbine drive mechanism. And
direct drive are very rare in terms of installed turbines in the United States, and I'm not sure there's a trend for higher numbers in the future. We've been thinking there might be, but we haven't seen it, at least in our data so far. I can't speak to outside of the US.
Great, thanks guys. So Ben, actually, I'm going to go back to you. I think there's an interesting question here. Ben, you're a resident expert on wind energy's impacts on residential property values. And someone asked, have you correlated sound levels or visibility to property value impacts?
We have not. The Berkeley Lab has not. That is, so visibility is relatively easy to characterize without doing a lot of high cost modeling. What we did for this study was very intense in terms of making sure we get this right. The models that are used for sound are relatively complicated. Visibility, on the other hand, can be done with desktop software. ArcGIS has a line of sight tool that gives you some sense as to whether turbines are visible or not. We have not done that recently. Our first study on property value impacts, way back when I started with the lab, did have me visiting every one of the homes and characterizing the quality of the view of the turbines, as well as the quality of the scenic vista in general. So that was included in that analysis, but it was a relatively small sample. When we came back and looked at the issue with a bigger sample, we did not characterize the views of the turbines. We just simply used distance as the proxy. And that's not perfect. In the European context, a number of researchers have looked at this issue and have found that when view is accounted for, there is, well, a general, in the European context, property value analysis has found statistically significant negative effects, not particularly large, but statistically significant. And they have found that there are enhanced effects, so slightly more negative effects when view is accounted for. So that's been done in that context. Still not sure whether US context is dramatically different from European context. Our past work has not found statistically significant effects. They could be there, as we've mentioned, but we just aren't finding them. They are relatively small or sporadic, I guess, or we would have found them. But again, we didn't look into view specifically. It's a good question. And I just will note that there are lots of ways to characterize view. It is of interest to us because it's not just, can you see it or can you not? And so in that first analysis we did, when we actually visited every one of the homes, we took into account a lot of different things related to the quality of that view of turbines. And if we do come back to that, we'll try to incorporate those things as well. Sorry, it was a long answer, Joe, but basically, no.
That's great. Thanks, Ben. I do want to note there are a couple kind of technical questions, again, relating to setbacks and things like that in the Q&A. So I would encourage people to check out the report for the full methodology where you can learn about those. But I want to give Ryan Darlow, looks like you're back. I want to give you the opportunity to chime in again about that turbine packing method and optimizing on annual energy output. Yeah, if you wanted to say any more about that. I think we missed your response there.
Yeah, and
Yeah,
Darla,
sorry
if you want to drop your camera just so you don't drop your voice, that might be a wise idea. That's perfectly fine. Where we got to was the difference in our results if we were to develop the project using a profit maximization technique versus an output maximization technique.
Yep. I was just talking away about that and then realized that my internet had dropped. So that's exactly right. The methodology used in this study was just absolute maximum capacity with very little consideration to profitability. So if there was space for an additional wind turbine in any situation, that wind turbine was added. So it didn't factor in interconnection. It didn't factor in the buildable constraints of a site, such as like, is the ground physically capable of it for whatever reason, like if there's some sort of ground constraint or interconnection or any of those other factors that any developer would absolutely be including in their process.
Thanks. I'm going to take over
more
the
detail if you need to.
Yeah, thanks, Ryan. There's a lot more to be discussed here. We are out of time, unfortunately, though. So we're going to cut off the discussion. My email is here. The report is easy to download. Please reach out if you have additional questions. If they're for Ryan Darlow, I'll make sure he gets them and responds to them if they're for others on the team as well. We really appreciate you attending today and asking such great questions. It's an exciting area of possible future work. And really appreciate all this, and as well want to thank again the U.S. Department of Energy Wind Energy Technologies Office for supporting this work. So I'm going to cut it off there. Thank you very much, and have a great day, everyone.